All right, so continuing, picking up where we left off before the first exam, we were looking at functions. So let's just do a really quick review of what we did with functions. Remember that functions are reusable units of code. They have a signature. Right? What's the signature? It's the return value, return type, the name, that is the identifier, and finally the parameters. Those are the inputs to the function, right? And this is the same in both languages. Let me make sure that the audio is working here. Right. Those are the same in both languages. But one of the differences in Java, for now, all methods will be public static methods. And again, that just means that they belong to the class. And when you invoke them, you go the class name dot and then the function name, just like math dot square root. Later on, we'll talk about member functions or member methods when we actually get into a little bit of object-oriented programming. But most object-oriented programming will be next semester. All right. What else in C? Right. You organize functions into modules. Right. The prototypes, and documentation, right, go in header files, right, files.h files. And then what else? The definitions go in source files, right, .c. And generally those will have the same base name, utils.c, utils.h. How do we end up compiling them then? You compile the library using the C flag. All right. So for example, if it was utils, it would be gcc-c utils.c, which produces utils.o. And then you can use that just like you would use -lm to link in the math library. You would link in your utils library by simply just providing the object file there. Ultimately, what you're going to probably, if it gets more complicated than that, you want to write what's called a makefile. We will provide makefiles for more complicated stuff. I think that you might see a makefile this week in your lab. We provide makefiles for certainly next week's lab when you have to actually compile with CMaka. Okay. In Java, in Java, you can further organize code into packages. For now, all of our stuff is going to be in the UNL SOC package. So any questions on that? We all brought up to speed with our memories, right? Let's take a look really quick here. My math, remember that I put the header files and all in the header file. I put all the documentation and its proper doc style comments here. That is /** and then a vertical line of stars, and then the last one ends with a slash there, //. It all goes above the signature. The signature ends with a semicolon. And then over in the .c file, we need to include anything that we end up using in our code. There really is no code over here, so you don't have to really include anything. But then we also include our header file. Remember what happened when we included our .c file? mymath.c includes itself. It got stuck in the compiler got stuck in an infinite loop. Because all it is basically a copy and paste. That's all this is doing. It's going out to this file, pulling out the contents, and then pasting it right here, replacing my include with it. Okay. But otherwise, I do not repeat the documentation. Okay. The DRY principle. Don't repeat yourself. I put the documentation in the header file. It does not get repeated here. But the signature does get repeated here. But instead of a semicolon, we have an actual body. Likewise, over here in Java, we did the same thing, but we called it mymath, right? And that's going to be upper camel casing. Everything was a public static method. That means that it belonged to the class. But otherwise, we didn't have prototypes. We just had the definitions. And the documentation here goes right above the actual function. Going forward, you will be required to document every single function that you write, right, using doc style comments. All right. Anything else on that? Otherwise, we previewed kind of unit testing, right? We talked about unit testing. What is unit testing? Well, a unit is a piece of code, usually a function. And then a unit test is simply an input-output pair that you feed into it. And then you check, does the actual output match the expected output, right? And we wrote a bunch of informal unit testing, right? That required us to do a lot of boilerplate. Create a variable for the input, or variables for the input. Then create a variable for the expected output. Create a variable for the actual output, and then have a bunch of logic that says, are they close enough, or do they match? What we're going to do now is look informally a little bit at formal unit testing, right? Formal unit testing means that you use a library to do most of the boilerplate code for you, right? That is all that code that I was copy pasting. Don't do that, right? Bring in a library to do something like that for you. Now in C, we're going to use, there are many libraries, but we'll use CMaka. I'll just bold it, CMaka. Now, what is the C for? Well, it's for the C programming language. Maka, the original name was Mockery, C Mockery. And the idea here is what is mockery? Well, it's mock data. What is mock data? It's fake data, right? It is testing data, right? You don't test on production data. Instead, you generate a bunch of mock data, a bunch of fake inputs, and then put your code to the test. Originally, it was put out by Google. Google abandoned it, and somebody took it up and open sourced it, and now it's called CMaka. There are several different other programming language or libraries for C, but this was at the time when we were deciding which one to use, this one was the most user-friendly for beginning computing students. Nevertheless, we are not going to require you to ever do any CMaka library from scratch, all right? Because it actually is quite complicated. Here's what you'll be working with next week, all right? So we have some boilerplate, not boilerplate stuff here, but we have some things like, for example, epsilon, right? We're going to have a tolerance built in. And we have functions to support that. Is it close enough? That is, is it within epsilon of each other, right? But ultimately, what we have here is something that requires a lot of pointers and function pointers, which is why we're not expecting you to write it on your own, right? We've provided this file for you. The actual exercise next week is to convert from RGB to CMYK, or CMYK to RGB. RGB is what you see on your screen, right? Red, green, and blue colors are mixed together to form millions of different colors. CMYK is what's used by printers. That's cyan, magenta, yellow, and then K is a level of black for dark or light, right? And so you have these two different colors. Those aren't the only two color schemes, by the way. There are, what would that be? I think that the projectors are different. They're not RGB. They're red, green, yellow, or something like that. You can see some old school projectors actually have three bulbs basically, and they're three different colors, but it's an additive kind of mix. In any case, what we've done is we've set this up so that there are CMYK values. There's a CMYK value. The 126, 255, 212, and then half tone black, right? Now, equivalently, if you were to, sorry, that's the RGB value, I guess. Yeah, with an equivalent. Okay. So the first three are RGB, sorry, and then these last four are CMYK. So equivalently, that would be half contribution of cyan, no contribution of magenta, and like an eighth of a contribution of yellow, right? With no black put into that, right? So you can that's our test case, right? This is our known input. This is our expected output. Now down below, what we do is we set up all of these unit tests. For example, bidirectional test values, we had to pass in aquamarine, then black, white, red, green, et cetera, et cetera, et cetera. Now you're going to have to write your own test cases in that you're going to have to come up with your own colors and use this as a basis to add things to it. We're not making you write this from scratch because, again, it requires pointers and function pointers, which we are going to cover. We're going to start covering pointers today, but function pointers, that'll be towards the end of the semester. So anybody can look at a piece of code and try to extend it, right? And that should be pretty easy. However, we are going to look at the version for Java in a little bit more depth, because you are going to come up with stuff, because it's much easier. You are going to come up with stuff on your own. So in Java, there aren't many libraries. There's the library. That's JUnit. And JUnit stands for Java Unit Testing, right? And for us, it's going to be 5.0. There have been many versions. 5.0 is the current version. I think it came out maybe 3 years ago or something like that. Lots of improvements. That's the one that we're going to use, okay? We do give you plenty of instructions on how to use this. For example, this is your Hack 6 next week. How do you install it in Eclipse? Well, it comes shipped with Eclipse. It's part of Java, period. So what you can do is you can right-click on your project in the Project Explorer, select Build. Come over here. Select Build Path, and then Add Libraries. And then you've got a whole bunch of options here. But what do you want to do? You're going to want to do JUnit. Right? Next, and then which one do you want? You want JUnit 5, right? And then finish this up. It didn't change any of our code. All it did is change the configuration of our project here so that now JUnit is part of the code. Right? I'm going to go ahead and create a new class here, and I'll call it my math tests. Right? Generally, you don't pluralize a class, but in this case, it's okay, because what's it going to contain? It's going to contain a series of tests. If I just called this my math test, that kind of tells me there's only one test, and so I have to make 50 different files, one for each test case, and I'm not going to do that. Okay. All right, let's take a look at an example. Here's your starter code in a couple for next week. Basically, what you do, and there's a bunch of other boilerplate stuff there. But what you do is you use what's called an annotation. This @test is a special thing that tells Java this function should be treated as a test. So what it does is it injects all that boilerplate code, if, else if, right? And then it counts up the number of passing test cases. It will actually generate the code automatically and insert that code as necessary into your code when it runs the tests, on the fly when it actually runs, right? So let's go ahead and look at an example here. Right? Remember my math, I'm going to go ahead and get rid of demo here. My math has that AGM, right? And what I want to do is I want to set up a first test for AGM. All of the functions are public void functions, and then you give it a name. So public void, what should we call this? AGM test 01, right? So it's kind of bad practice to use 01, 02, 03, etc. But it's kind of usual practice in unit testing, because I'm not going to put on that tests 6 and 5, right, and 5 or something like that, right? That gets way too verbose. All right, so I'm just going to keep it simple, 01. Why do I start it at 01? So does anybody know an old programming language called BASIC? Have you ever heard of that before? In BASIC, you would do something like this. 10, print hello. Right? 20, print world. And this is, of course, not real, right? 30, go to 10, right? So I'm now stuck in an infinite loop here. You numbered your lines manually in BASIC. And you always went by tens, because what if you had to go back and fix your code and add another line in between it? Well, if I had gone, say, 1, 2, 3, I'm renumbering every single line in the file. So one trick was to go by 10, so that if you ever needed to add something, you come back and you have some room there, 15. Now, if you ever add 9 lines of code between those two, now you're screwed and you have to realign everything and renumber everything, right? It was not something that was copied in any other programming language. Why am I starting it out at 0? Well, because I want things to align, right? If I know that I'm gonna have like hundreds of tests, I would probably start it out with 001, right? But I know that I'm probably gonna have more than 10 tests here, and so I'm gonna go ahead and go 01. You do this with file names too, right? So that it all lines up. Otherwise, file 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, where does that end up? It ends up here or something, like out of order entirely. So always prepend with zeros in computer science. Now let's go ahead and create some variables here. Double. Well, what does AGM take? It takes x and y. So x is equal to 4 and double y is equal to 6. I forget what we were testing. What would the AGM, here, let's look up that Wikipedia article, Wikipedia AGM. We'll just steal their test case, remember that? Right? That's what we did first, right? It was what, 24 and 6. And then there is the actual number, 24 and 6. And let's come back over here, 24, there we go. So I'm going to also go ahead and create my expected output is equal to that thing. Okay, that's way too many digits of accuracy. I'll go ahead and just cut it down there. Okay. Now what I need to do is I need to create the actual output, a double actual output, right? Is equal to a call to mymath.agm of x and y. Right? There. Yeah, go ahead.
Would the spaces in the expected output effectively?
No, well, it's not going to let me compile apparently. Oops. That was 4, hopefully. There we go. There. Something like that. All right. All right, so now how do we actually test here? Right? We need to go back to our example over here. Right? And let's see. I want an assert equals. Assert equals. There we go. Assert equals. And then you have the expected and then the actual result. So assert equals the expected output. There we go. And then the actual output. Right. There we go. And I need to bring this in. I need to, no, I want, darn it. All right, I'm just going to grab all this up here. I want all of this stuff. There we go. And copy, paste. There we go. Now you know what assert equals is. Okay. Now if I were to run this, it's not going to run because there's no main, right? JUnit tests are completely different. JUnit tests don't have a main. Instead, when you say run a program as JUnit, you specify, I want to test that test file, or I want to run that test file, and that test file. Or all of these test files in a particular package, right? Remember that it's not a test unless it has that annotation up there, right? Now it's a JUnit test. Now when I hit run, it will actually run. It'll run it as a JUnit test file. And it'll come up with a report over here, if you want to see what that report looks like. Red means it failed. Right? There were 1 of 1 tests run. There were no errors, but there was 1 failure. Let's double click on that to find out what the failure was. Come on, where is, well, okay, that takes me back to the assert equals. They were not actually equal, right? Why? Because we haven't built in our tolerance yet. Right? We'll come back to that here in a second. But otherwise, you can look at the error message here. There we go. So there on the left is the expected. There on the right is the actual. And you can see that they start to disagree after about, I don't know how many digits of accuracy that is, but it's far more of the digits of accuracy than we were hoping for. All right. Let me show you what it would look like if we were actually testing something with integers instead. Once again, start out with that, that annotation there. Public void, let's see, factorial test 01. Right. Okay. Remember that we also wrote a factorial function here, right? And factorial of, say, 5. Let's do that. So int x is equal to 5. Here there aren't 2 inputs. There's only one input and one output. So int expected output is equal to, and then you can truncate these to just expected and actual if you want to. What's the factorial of 5? 5 times 4 times 3 times 2. 120? All right. Or you just believe in me? All right. Int actual output. Output. We will make a call to my function, my math, factorial of x. Right. Now let's assert equals on the expected and the actual. Right. And note here that I'm not I'm not counting up the number of I don't have all that boilerplate stuff of if else if. Right. That's all encapsulated inside that assert equals. I don't have all of the boilerplate of adding them all up and printing error messages and stuff like that. Let's run this again. Now you see 2 out of 2 tests have been run. No errors. There was still that one failure that we have to take care of. But you see that over here, this is now green. You can, if you really focus in there, you can see there's a green check mark. That means that it passed. There is kind of a blue X right here, and that means that it fails. Ultimately, what you want is 0 failures and that it runs all the tests. Okay. So what do we have to do to make sure that that other test case is passing? We need an epsilon, right? So there's my tolerance. Now our tolerance of hundredths, that's probably not going to be acceptable here, right? Let's go ahead and make that tolerance, and then I'll take a tolerance for values. All right, there we go. And I don't know, what did we do before? Something like that, right? Still not going to pass because we're not taking that tolerance into account. So let's see how we do that. Epsilon, there we go. It's the same assert equals method here, but with an additional parameter here. Do you remember what allows us to do that in Java? We can have multiple functions with the same name. That's overloading, right? So there's epsilon, and then optionally we can actually put a message here. Not close enough. Right? That's going to be printed in the event of a failure. In this case, I think that it's going to pass now, though, right? And so now it's 100% green. Right? If we had required, I don't know, way more, or here, I can make this test fail. What if it's 14? Right? Now my test case is wrong, right? But I can still look at this. There we go. Not close. You see that? There's my custom error message there. Not close enough. Right? And then I can still click on it and see, oh, it disagrees at the the tens or the tens place there, or whatever that is. So let's undo that. There we go. I can add as many as I want. I can go and fix my code, right? I can add error. I can add error handling and then do testing for error handling. That's what we're going to do eventually, right? JUnit is way more flexible than CMake, and so you'll be able to do a lot more with JUnit than you will with CMake, but that's probably true of Java in general, right? You can do the same stuff in C. It's just that you're going to be writing a hell of a lot more code to do so, right? I'm kind of bummed actually that it seems like CMake, the development cycle is kind of stagnated. They've got a lot of feature requests, some feature requests from me, and that they have not done yet, right? And I'm not going to do them. It is an open source project if you want to contribute to it, though. Right? All right, so that's CMake and JUnit, and you'll be using. And again, the instructions you can rewatch the video when you get to those. Otherwise, the instructions for doing all that stuff is pretty much in the handout right here. If you don't want to install, and one other thing I would mention is an optional project setup. This is optional. So in larger projects, typically you don't want your testing code and your production code in the same location. You want to separate them out. And so you can do that. Generally what you would have is a source test Java folder, and then a source test, source Java, I think it is, source main Java, that's it. That's the convention. So right now we just have one source file and everything is in the same source file. What you would do optionally if you want to is that you would separate them out so that when you actually go to build your stuff, you're not including all the test stuff with it. Right? All right. All right. Any questions? No? Then let's talk about something that is wholly and uniquely C, called pointers. Right? Now, before we do this, let me go ahead and show you a picture. Here's memory. Right? I can zoom in a little bit on this. What consists of memory? Memory has an address up at the top here, and then the actual contents of that address. Just like physical addresses, right? Somebody lives in 1234 A Street. Well, there's an address to that street, but then somebody actually lives in that street, lives in that house, excuse me. You'll note here that I'm using hexadecimal, but if you actually look at each one of these things, it's only, let's see, 1 octal away, right? So if you count, it go A, B, C, D, E, F, G, all right? C, D, E, F, And then what happens after? Well, now you've got a carryover, so 7 becomes 8. Now it's 0, 1, 2, 3, 4, dot, 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 and it starts counting up again, right? Not all things are equal. For example, if you just have a byte of data, right, then you have something like this, right? Or this might be a word, I'm not sure. I'd have to think about the addressing over here. But some things, here, I guess we've got a picture of it. Some things like a double, those take 8 bytes. And so you have 1, 2, 3, 4, 5, 6, 7, 8. So in this model, it's called byte addressing. You can, what is a byte, by the way? How many, so a bit is 0 or 1, 0 or 1. But then a byte is 8 0 or 1s, right? Okay. And so what we've got here is 8 of those things, so that's 64 bits in a double, right? That's why it's called a double. So it takes all 8 of these bytes here, all 8 of these addressable bytes here, okay? An integer, however, only takes 4, so it takes half as much room, right? Each individual character, say hello, and then the null terminating character, which we'll talk about later on, each one of those takes 1 byte. Otherwise, it might be some not human readable data at all, right? It just might be some code or something like that. The key here is, however, that memory consists of an address and the contents. Everything that you've been doing up to this point, int x is equal to 42, you have only been playing around with the contents. Now you're actually going to start playing around with the addresses, right? This is something that is unique to C, right? Something that only C allows you to do, or C++ too, but that's because it's C, right? So again, memory in a computer has both an address and contents. An address is a numerical designation of where the data is stored. Right? Now, you might traditionally think of memory as, a bunch of DIMMs, right? That's double inline memories. If you've ever built a computer, how many people have not built a computer? Or have not played around with the internals? Like, you at least have the window in the computer, right? You can see the fans and all that stuff, right? All right. So you have memory, right? That's RAM, random access memory. And it usually comes in DIMMs, these long things, and then you put them into the sockets, right? That is called main memory, right? That's RAM. It's actually quite slow, right? Because you have this memory model where you have RAM, then what's below it? Where's everything stored that's not in the main memory? Your hard drive, right? Or your what are they called? NVMs? NVMe, right? That's much faster because there's no moving mechanical parts. And then, SSDs and all that stuff. But still, traditionally, what the mechanical hard drives are still the cheapest, right? Per megabyte. Most reliable? Oh, really? Why? I would expect mechanical failures rather than cheapest and biggest.
You get like up to 10 terabytes.
Yeah, and
Technically, they last longer, but
the mechanical ones do.
technically.
Okay, all right. What's actually the cheapest? This will blow your mind. Nope. Tape. Right? Still, per megabyte or per gigabyte, those big giant reels of tape that from the 70s or 60s or whatever, those are still the cheapest. You can still get them if you really try hard. We have tape backups from several years ago. I don't know if we use them anymore, but those are still per gigabyte the cheapest way of storing data long term. Right? You take something and you put it on a big reel of tape, you put it down in a salt mine, and it'll last forever. Right? And that's what they do.
That's what the line is.
Until the mine collapses. All right, you put it in salt mines because there's no moisture. The salt absorbs all the moisture. But in any case, that's what's below, right? Then you've got main memory RAM. What's above it? Your processor has memory on it, right? In fact, there might be several levels of, it's called cache memory, right? And there might be several levels within your processor. Really, really expensive, but really, really fast. Less expensive, but slower. Even less expensive, but way slower, right? And so there's always this trade-off of for memory of cost versus speed, right? But for us, it's all the same. There's an address. Whether or not that happens to be on the hard drive, whether or not it happens to be in RAM or on the cache, that's the operating system or the hardware's responsibility. We just have a number, an address. Okay, it's called a virtual address. Right. Contents of the contents are the actual data that's being stored. Say an int x. Right? Pointers in C allow you to access and manipulate memory locations and their contents at the same time. Normally, if I just go int x is equal to 42, I'm only working with half of the memory, the contents, not the address. So let me come over here to our demo, and let me show you how to start doing that. By the way, none of this is available in Java. Java does not have pointers. Java does not want you to have pointers because pointers are extremely powerful, right? And with great power comes great responsibility. If you can go ahead and directly manipulate the contents of memory, what is to stop you from writing a program that accesses memory that doesn't belong to you, that has security issues, right? Most programming languages don't allow you to do this. And a good operating system, even in C, would not allow you to do this illegally, right? It's called a segmentation fault. We've heard of that before, right? You probably you've experienced that before, right? So let me come over here and let's go ahead and get rid of all this stuff now that we're good on it. Right? And here is a regular old variable, right? Int x equals 42, right? That's how I can go ahead and assign the contents of some memory location, right? Now, let's go ahead and create a pointer. Create a pointer variable. Not a regular old variable, but a pointer variable. And we'll make it point to an integer. To do that, we use the star operator here, okay? Now, at this point, what is P pointing to? That's why I call it P, because it's a pointer. What is it pointing to? Could be anything. It could be that dead beef. It could be null, and we'll talk about null here in a second. It could be a random memory location that doesn't even exist. It could be a random memory location that exists but doesn't belong to you, right? Could be anything. It could be, say, a valid memory location that doesn't belong to you. On invalid memory location, right? What's the other possibility? A valid memory location that does belong to you, but you'd end up screwing up your own program, and you can do that, right? If you've got a program that prints "Hello World," right? Well, printf, that's a command that exists somewhere in your program, is somewhere in memory. If you go to that memory location and start mucking with it, right, then bad things can happen. In fact, it's called a stack smashing event, right? And you can smash your own stack basically. And so you can screw up your own memory. You can attempt to access memory locations that don't belong to you, in which case the operating system is going to say, nope, I'm not going to allow that to happen. Kills your program with a segmentation fault. Or it could be an invalid memory location that, I've only got like 64 gigs of memory, and I try to access the 50th terabyte or something like that. That ain't going to work, right? Because that memory location does not exist. Okay. All right. So let's make it point to a valid memory location. The first memory location that we're going to make it point to is null. So P is equal to null. Now in C, NULL, all uppercase. Java, null is going to be all lowercase NULL. Right? What this is, and I put that into quotes there, a valid memory location, it simply means it's a placeholder for an uninitialized pointer. Right? Later on, you can check for it. You can do what are called null pointer checks. Null pointer checks. If P is equal to null, again, all uppercase, then we can issue an error message, right? Cannot access the memory location for P. Right? We can check for it and do some preventative programming, right? Where to access that memory location and its contents, it's got to be valid, right? There's really no way for us to tell what's valid and not. That's the operating system's responsibility. But one thing that we can check for is null. And so generally you'll be doing null pointer checks. If it's null, you can't do anything with it, okay? Now let's make it actually point. Let's make it point to an actual memory location. Memory location. There we go. Now to do that, what I can say is P is equal to ampersand A. Remember A? Or I guess it was X, sorry, X. Okay. What are we doing here? Well, ampersand in front of a regular old variable gives you the memory address of that variable. So in the left-hand side here, left-hand side, it's a pointer, which is equal to a reference, which is equal to a memory location. Right? Likewise, the right-hand side, because we've got that ampersand in front of it, ampersand makes it into a pointer, into a reference. So all three of these things are essentially the same thing. A pointer, a reference, a memory location, a memory address. Right? Memory address. Okay? Now that I've got a pointer to it, I can actually manipulate the contents. Right? Manipulate the contents through the pointer. Right? So I could do that by saying just x is equal to now 43. Right? That's how we've been doing it up to this point. Right? We're now going to do it through the pointer. Right? P is equal to 44. But I can't do that because the left-hand, look at the first one here. The left-hand side, x, is a regular old variable. The right-hand side is a regular old value, 43. Now look at the second one here. The thing on the left-hand side is a pointer, but the thing on the right-hand side, is that a memory location? Technically, there is probably some memory location that has a designation of 44, maybe. Right? But does that likely to belong to us? If I just mash my keyboard here, right, and that's some random memory location now, right? So I can't do that. Instead, what I have to do is I have to dereference the pointer, right? So star in front of a pointer variable dereferences it and makes it into a regular old variable. So you can assign it a value, right? Value, there we go. Right? Okay. So star, when you declare it, makes it into a pointer. Star afterwards basically takes the pointer away and makes it into a regular old variable. A regular old variable with an ampersand in front of it, and by the way, we've seen that before, where? You remember scanf? Yep, scanf and maybe something else, I'm not sure. But that's what it was doing. It was getting the memory location of that variable, so you could pass the memory location to the function, which we'll look at next time. Right? But what I want to do is I want to show you how all this works, right? So printf, x is a regular old variable with value %d, right? That's what we've been doing up to this point. There we go. Printf, p is a pointer variable at memory location xx. We'll come back and fill that in with value stored in it, with value yy. There we go. All right, so how do I get a memory location here? Remember the placeholders, %d, %f, %c. Some of them make sense, some of them don't. I'll give you a hint here. This one actually makes sense. It's %p because it's a pointer. All right, there we go. And what is its value? Well, it's a pointer to an integer, so that would be %d. Now, how do I provide this? Well, p is already a pointer. So if you want to treat it as a pointer, it's just by itself. But if you want to get the value stored at that memory location, you have to take that pointer and then you have to make it into a regular old variable, which would be star in front of it. Okay. Now let's go ahead and take a look at this demo so far, and then we'll do a little bit more. GCC demo.c. There we go. A dot out. X is a regular old variable with value 42 stored in it. P is a pointer variable with memory location blah with a value 42. Right? Let me show you that it's exactly the same memory location as x. Printf. X is a regular old variable still with that is stored at memory location %p. That's always going to be formatting it as a memory location. Now I've got x here, but if I were to print out x, I would print out 44 because that's what's stored in the contents. How do I take a regular old variable and make it into a reference variable so I can get its memory address? Ampersand. So just, it says you're going to have to, it's like, I always liken it to calculus. Many of you are in calculus or have been. When I was in calculus, I could never remember what's the derivative of sine? Cosine, right? And what's the derivative of cosine? It was sine, and okay, which one did the negative go on, right? And I just put it on a post-it note and put it up on my desk until it was drilled into my brain. And that's how you have to memorize this too. What does the star operator do? What does the ampersand operator to do? And in what context? So once again, let me go ahead and run this and show you that the memory location of my pointer, that my pointer is pointing to, and the memory location of x, they are the same. Because p is pointing to x, right? And they both have a value of 42. Here is the actual, I've got different variables here, but here's a picture of it, right? So I use ptra instead of p, right? But there's some memory location, and it's null initially, because that's a pointer variable. You can make that pointer variable point to a, in this case, by using a ampersand. Well, a is stored at memory location C260EC84, and it has a value of 10. So what I've done is I've changed this null to that memory location, 260EC84. And now it's referencing this memory location right here. And that's why we call them pointers, because it's pointing to that memory location, right? Which still contains the value 10 here, or 42 is what I did, 44, right? Okay. There are some gotchas, right? Once again, what if you were to do something like this? P is equal to 42, right? Yeah, let's try to now see what's in there, right? So what I'm going to do here is I make it point to memory address 42. Does that belong to me or not? I don't know. I'm going to leave that print off just for a second here to show you that, well, first of all, I get a warning, even without the wall flag, right? That doesn't make any sense. That 42 is not really an address. Are you sure you know what you're doing there, right? Yeah, okay, I know what I'm doing. Let's go ahead and go forward. It's probably not going to manifest itself because I'm not actually doing anything illegal yet. I'm simply just saying memory location 42. I'm not actually going to that memory location and doing anything. Let me restore this now. And I am doing something. I'm going to that memory location and I'm getting the contents. I'm jumping from that address over to 42 and trying to pull out what I think might be there, 10 in this case. Right? Now let's try this again. GCC, same warning. What's going to happen here? Hopefully, segmentation fault, and it does. Right? Why? I try to access an illegal memory location, one that doesn't exist or one that doesn't belong to me. And so it says, nope, that's illegal. Because imagine what if you could do this? Right? You could access any memory location, including, say, whatever the web server is running on, and grab all the passwords or whatever in plain text or SSL keys or something like that. Right? So this will lead to a segmentation fault. And what is a segmentation? Well, a segmentation refers to a segment of memory. A fault means something that you shouldn't be doing. And so you're trying to access memory locations that doesn't belong to you, and consequently it kicks you out and kills your program. Right? You can do other things. Say P is equal to, I don't know, main. There we go. So this is really weird. Very weird. Right? Make the pointer point to the memory location that stores the main function. Right? Because what else is stored in memory? Functions are stored in memory, right? Because you're running them, right? So let me go, that's how you do a function pointer. We'll talk about that later on. Now let me go ahead and try to dereference it. So I'm probably going to be able to do this. P is a pointer at memory location whatever with value whatever. Let's find out what happens here. There we go. It was perfectly fine because that's my memory. Main is my memory. I'm the program, right? And so it's main is actually located at this memory address, and it's attempting to take whatever 4 bytes are there, marshal them into an integer, and then interpret them. That's of course garbage. If I were to run this again, would you expect the exact same numbers? Let's move this up. Looks like the exact, nope, not the exact same numbers. The exact same number over here, but I'm talking about the exact same memory location. Why is it different? In fact, if I keep running it, it will be completely different every single time. Think about what the operating system is doing. In fact, I can show you. There are hundreds of applications running at any 1 second, right? There are things that are being born and using memory, quitting, and then giving that memory back to the operating system over and over and over again every millisecond, right? So there's a whole bunch of stuff that's going on in the background there. Like this one is using 42 gigabytes of memory right now. That one's only using 28, like 2K or something, whatever it is. It's running a shell over here. Node is probably an instance of Node.js, maybe, I don't know, right? But Bash or whatever, right? Go in a larger system and you'll see a lot more stuff going on, right? I don't know. We can take a really quick look, right? But while I'm doing this, why is it a different memory location every single time? Well, because memory is being used and unused and reused and unused and all really, really quickly. And so it gets loaded up in another memory location when I run it a second time. I'll show you another HTOP here is better. It's nice and pretty. All right, not many things going on today here. What is NetHogs? I have no idea what NetHogs is. But these are the users over here, right? There's me at the top. I'm using HTOP right now to show you this stuff. And then all these people are running a bunch of different stuff over and over again. I don't see anything interesting though. Oh well. If we went on our web server, I'm sure that you'd see a bunch of other stuff. But by the way, you'll play around with that stuff when you do the PDC modules, which you can start doing at some point. You don't have to do them right away, just by November, right? Sometime. All right, let me go ahead and quit out of that. And once again, if I run this again, it will run in a different memory location almost every single time, right? The odds are astronomically against you that you would end up running it in the same memory location, right? But now why is it not complaining here? Well, because it's my memory. Let's make it complain. P is now equal to 123. What does that do? That replaces part of my main code with a random number, 123. Right? Let's see if it survives after that. TCC, and let's run. There we go. Still, now it's a segmentation fault. I'm kind of surprised it didn't say that it was a stack smashing event, because that's exactly what I'm doing. When you run main, it gets loaded up in the stack, right? And remember, you've got stack frame on top of stack frame on top of stack frame. Well, if you go and you start changing the dishes at the bottom, right? I'm smashing my own stack, and it detected that and gave me a segmentation fault. But often I've seen it actually come out with a stack smashing event occurred. Yeah.
Could you just say the parent number?
Say what?
Can you just say like the parent, not like the value main?
No, at this point, it's pointing to main, whatever that memory location that stores main. And so there's code for main in binary, and I've changed the first 4 bytes of it to 123. So now it's completely not interpretable by the machine, right?
Okay.
I mean, it is. It's just gobbledygook, right? All right. All right. We'll pick it up there on Wednesday.